And welcome, everyone. Welcome to chemistry. This week, the first lab rotation begins. So if you have a lab this week, check the course outline, check to see what section you're enrolled in. You can look on OWL to find your location, your personalized Achieve link, and you get to start with lab number 1. This is an opportunity to apply some of your Chapter 1 self-study concepts, as well as build your familiarity and skill set in our chemistry labs. You get to explore density and complexes and mass percent, learn how to use some of the glassware, have a tour of the lab and figure out where all of the important instruments and safety materials are. So this is a great lab to get oriented to the lab, and I'm sure you will enjoy it. Okay, last class, we began our conversation on electron configurations of ions. We worked through the first 2 examples with vanadium and gallium, and my question for you to kick us off today is, what is the correct ground state electron configuration for manganese 2+? Chat with the person beside you. I recommend starting with manganese and then turning it into manganese 2+. I'll give you 1 minute. And 10 more seconds. And 3, 2, and 1. Okay, most people going for A, and I agree, but we're less than 70%. So let's see how we got there. First, we find manganese on our periodic table. I have it up over here on the document camera. It's handy to write the abbreviated electron configuration when that's an option. So I go backwards from atomic number 25 until I hit the most recent noble gas that we just passed. That tells me that argon is the most recent one. So rather than writing out 1s2, 2s2, 2p6, and so on, we can just write argon in square brackets. Then, since argon, we've added 1, 2, 3, 4 s, 2 electrons there, so 4s2. And then we hit the 3d block. And how many electrons there? 1, 2, 3, 4, 5. That would be the neutral element, 4s2, 3d5. But then we remember that we have to turn this into manganese 2+. We have to steal 2 electrons away. And we have to remember that when we steal electrons, they must come from the highest principal quantum number. So rather than removing by the filling order, we just added electrons, the most recent 5, to the 3d orbitals. When we do that, in reality, what happens when we're filling up, we fill up at 4s2 and then the 3d. But once the 4s2 is filled and the 3d starts to be filled, the energy levels of these 2 orbitals flip. And so 3d comes lower, 4s goes higher. So when we remove electrons, we need to remove them from the higher principal quantum number orbital, which is 4s. The charge is +2. We can't remove protons or add protons. We can only remove or add electrons. So we're going to take away these 2 electrons in the highest principal quantum number orbital. That is the 4s, which leaves us with our 5 3d electrons. So remember, when we're removing electrons, we always remove them from the highest principal quantum number orbitals. Okay, so we have learned how to write out electron configurations for various elements on our periodic table. I've had a number of questions about exceptions, and yes, there are exceptions to these rules. We can use the periodic table to see where the S blocks and P blocks and D blocks are, and F as well. Sometimes there are exceptions. Right now, we're not being mindful of the exceptions. In a couple weeks, we'll teach you 2 exceptions. There are more exceptions than that in the periodic table, but for our purposes, we're looking on the big idea, and we don't have to worry about exceptions quite yet. Okay, so we know how to put these electrons in different orbitals, how the energy increases. We know how to make ions, but now we need to think about how the electrons are being placed in some of these degenerate orbitals. And we introduced that term last class. Orbitals that have the same energy. For example, the px, py, and pz, the 2px, 2py, 2pz, they're just different orientations of the same orbital that has the same energy. All px, py, pz, those are degenerate. Our 3d orbitals that we learned about, those are also degenerate. They have the same energy level when they're in an atom all by itself. So how do we place electrons in these degenerate orbitals? Well, we're going to do a little thought experiment. Imagine you're going to the doctor's later today. And at the doctor's office, there are 3 benches, and each bench fits 2 people. You're feeling a little sick. There's already one person there who looks a little sick. So, by show of hands, which bench do you want to sit in as you wait for your appointment? Hands up for bench A. One person's already there. Hands up for bench B. Bench C. Okay, most people go for bench C, and I would agree. I'd probably sit as far away as possible as well. But you know what? Any of those empty benches, sure. We got a little bit of personal space. I would sit in one of those as well. Okay, now you go into the doctor's office, and there's someone in bench A, and apparently the identical twin in bench B. We're going to vote. Where do you want to sit? Who votes for bench B again? What about bench C? Okay, and I would agree. I would want to sit all by myself and have as much space as possible. But you walk into the office, there's someone in all of those double benches. Where do you sit? You know, if you could stand, I'd probably do that. But if you had to sit somewhere, well, you have to find a spot to sit. So you have to double up. It'd be a little bit uncomfortable, right? Any of these options, they look pretty identical to me. It's going to be a little uncomfortable, a little bit icky to have to sit really close to someone. But you'll deal with it and life will move on. Electrons do something in a similar way. If we have degenerate orbitals that are available, same energy, why double up when you can spread out and have your own orbital, have your own space? That's what electrons do as well. They singly fill up the orbitals to have those different wave functions, but when they have to pair up, yes, they will pair up. It requires a little bit of energy to pair electrons. It's a little bit uncomfortable, a little bit less stable to have to pair them, but we do so. So for example, if you were walking into an office here and you have to sit somewhere, but you could walk 2 buildings over to find another spot at a different library, that's a lot more energy, a lot more inconvenient to go to another building. You'd probably just pair up. So we still fill up these orbitals that are degenerate at the same energy level. We pair them up before we go to the next energy level. So we can represent electron distribution in these orbitals. Some of them are degenerate orbitals. by showing where the electrons are hanging out. And this is governed by Hund's rule. When we have degenerate options, we have orbitals that have the same energy level, you know what? Let's use those all up, spread ourselves out, electrons stay unpaired as much as possible, but when they have to pair up, then you can pair them up with opposite spins. When they're unpaired, they typically have the parallel spins. So they sit the same way. So if we only have one electron in a 2p orbital, we can put a little arrow in one of those boxes. Px, py, pz, I don't care. Choose one if it's an atom by itself. Add the second electron. Sure, it could go in the next spot. Add a third electron. We have spread those electrons out across the degenerate px, py, pz orbitals. Well, you have to add an additional electron. You're going to have to pair one of those up. And so on as we add a fifth and sixth electron. We pair them up before we jump up to the next higher energy orbitals. So let's wrap up this final example. We want to draw ground state orbital diagrams for the valence levels of arsenic and bromine. And we want to show all the orbitals and electrons in these valence levels. Then we'll answer which element has the greater number of unpaired electrons. So let's start with arsenic, As here. I've written out the electron configuration because that's something we learned about last class. We already know how to do that. So most recent noble gas is argon, and then we add 4s2, 10 electrons in the 3d orbitals, and then 3 electrons in the 4p orbitals. We just want to draw the valence orbitals for our diagram. Sometimes it's called an orbital box diagram. Sometimes it's just called an orbital diagram. You can see we weren't using boxes, we were just using lines. Either way, we're still showing where the electrons are hanging out. So we have valence electrons and we have core electrons. We need to remember that definition from last class. For the main group elements, electrons with the highest principal quantum number are our valence electrons. So the s and the p electrons are our valence. The 3d and all those electrons in argon are our core electrons. The question says we can just draw the orbital diagram for the valence electrons. So I'm going to keep it simple and just do the valence. So there's my 4s orbital and my 3 degenerate 4p orbitals. In my s orbital, I have 2 electrons, one with an up spin, one with a down spin. They have opposite spins. Remember that fourth quantum number, plus half or minus half? They have to be different. So if one has an up, the other has a down. How do we know whether it's up or down if it's just one? Meh. If we don't know anything else, we don't really know. But if we know one has the up spin, the second electron must have the down spin. So we have our 2 electrons in the 4s orbital, and then we can see we need to add 3 electrons to the 4p orbitals. So I add my first electron, and my second, and my third, spreading them out across these degenerate equal energy orbitals. And here I can see I have 3 unpaired electrons. Okay, so let's compare this now to bromine. Again, I've written out its electron configuration because that was last class's lesson. We have our 4s and 4p electrons that are our valence electrons. So I'm going to write out my 4s and my 4p orbital diagram. For us, I have an up spin and a down spin, so 2 electrons with opposite spins. And then for my 4p, I have to place 5 electrons there. So 1, 2, 3. First 3 go unpaired, spread out, feeling good about their personal space. But the next 2 need to pair up. Little bit uncomfortable, but they'll handle it just fine. 4 and 5. So how many unpaired electrons do we have? Well, now we just have one unpaired electron. Now, if this question asked us how many total electrons do these species have, which one has the most electrons, bromine would have more electrons. It has 5 electrons in the 4p orbitals, but it's asking us about unpaired electrons. So arsenic is going to win with 3 unpaired electrons. So which one has the greater number? Arsenic. 3 unpaired electrons. Okay, so in topic 2.1, we've explored how electrons are existing, what they're up to inside of atoms, what these orbitals are, how we can write out these electron configurations. And now we're going to take a step back and look at comparing different atoms across the periodic table. We now get to jump into periodic trends. We're going to be looking at our periodic table and seeing what we can learn about elements from that. So to kick us off on our new topic, based on your previous chemistry knowledge, how are elements arranged in the periodic table? Chat with the person beside you and answer your option. That's why we only have 70% for minus 1 or 2. There's only plan for 70% that chance. Yes, I'll answer that in the question. They're on owl. Okay, and 10 more seconds. Okay, and I'll leave that open for a few seconds. As you turn from the end of topic 2.1 to topic 2.2, did you notice a bunch of practice problems? Yes. Who has started those practice problems? Who has finished those practice problems? Okay, that was way too few hands. It's okay if you didn't finish them. We just finished topic 2.1. But starting them is definitely something that should be on your radar already. I would say sit down at least twice a week and work on those practice problems. Now that we're finished 2.1, make sure you get those done this week. You want to work through, you don't want to work for like 6 hours. I would hate chemistry if I had to do practice problems for 6 straight hours, but work for like an hour or 2 at a time. Work through those practice problems. That's how you find out if you understand these theories and can apply them to solve new problems. So make sure you put solving those practice problems on your homework list for this week. The answer keys are available on OWL, something under workbook practice problems. It is on OWL under content. But don't just look at the answers because that just gives away the work and the thinking process. Looking at a problem, not knowing what to do, thinking about it, looking through your notes, chatting with a friend, figuring out is where the learning happens. So make sure you focus on completing those practice problems. Okay, where did we go with this one? Okay, so many people chose B, and I agree. No one chose A, thank you. Definitely not. C, yes, that's how it was originally conveyed. Yes, by chemical and physical properties, and yes, even by electron configuration. Okay, so again, not a great exam question because there are multiple correct answers. The cool thing is the periodic table was built and designed before scientists knew about atomic number, before they knew about the number of protons. We can now use our periodic table to figure out electron configuration. I showed you that today and last week. They figured out the periodic table before they knew about electron configurations and electrons, which is amazing. So as much as I love that it's ordered by atomic number and that it's ordered by electron configuration, it was built based on mass, or what they assumed to be the mass, and the chemical and physical properties, which is fascinating. The periodic table is a work of art, and it is a work of science, and it is one of the most spectacular conglomerations of scientific knowledge that we have in our history. It gives us a way of understanding matter, organizing matter, identifying stuff, and we can learn so many chemical and physical properties and predict aspects of stuff and matter based on where it is on the periodic table. Now, before you feel stressed out, this picture is not in your notes, so this is not testable. Don't worry about this. But I think it's really cool, and I knew you could handle it. The periodic table that we know today looked a lot different when scientists were working together and working independently and trying to figure out how to organize matter. One of the cool arrangements that was proposed was that elements were kind of like musical notes. Who plays an instrument here or sings? Okay, lots of you, and I do as well. I play the piano and I sing. And if you think about music, you have the octave scale, like the C major scale, you go all the way up, and it's built on an octave. So every 8 notes, you hit the C major again, right? Elements, as you go across the periodic table, at least the main group elements, as you go to number 9, it's like you're starting again. And the physical and chemical properties tend to repeat periodically. That's where we get the name of this from. And so someone proposed, you know what, maybe it's this like natural law of music and it's octave scales. Every 8 notes, you get a repeating pattern happening, which is cool. It didn't stick, unfortunately. Another proposal, again, it's not in your notes, it's not testable, don't worry, was a telluric screw. Courtois proposed, again, this repeating pattern. And we know about the repeating pattern as we go down the periodic table. We have similar reactivity, similar ratios and reactions. And so he said, you know what? It's kind of like a screw that every time you go around, the elements, actually, I don't think they knew they were getting bigger, but they have these repeating properties, which was also really cool. Unfortunately, he wasn't a great communicator. This was his publication and no one could really make head or tails out of what he was saying. This is now like the Wikipedia article, nice view of like a 3D image of a telluric screw. Didn't stick either. But Mendeleev's periodic table, this was his original version that he sent out like 200 copies to a bunch of colleagues and scientists and said, this is what I have worked on. And he was, jumping off of ideas from other people as well. Mendeleev left spaces here. So you can see like there's question marks there. And Mayer also left question marks in his version of the periodic table, where they were gathering what they understood about different elements. So they were taking stuff. I mean, they didn't understand compounds versus elements. They were trying to do reactions until the properties didn't change anymore, and then take different masses and compare them and see how the ratios reacted. And anyway, they ended up identifying all these different elements, but they left spaces saying, you know what? We don't have an element that we know of that fits in this mass range with this type of property period that we have happening. So scientists are like, this is cool. I'm going to go look for that. And that's how they found some of the elements that hadn't yet been discovered, because they knew what mass they were looking for. They knew the type of chemical properties they were looking for. Pretty cool. This early version of the periodic table is like inverted and flipped from what you're familiar with. So you can see in the purple box, fluorine, chlorine, bromine, iodine. We know that goes like down on the right-hand side of our periodic table. He had it going this way. But they arranged it based on mass and chemical properties, how it reacted. It was pretty cool. It is a work of art. And this is kind of what we have now. But you'll be like, that's not what's on the back of my workbook. But this is just a visualization of what I mentioned last class. If we tucked that F block into the periodic table, that's where it would kind of go. Somewhere around here, whether you include those ones or not. But obviously that doesn't fit on an 8.5 by 11 sheet of paper very nicely. So we pull that F block out, put it below, and then we have our beautiful version of the periodic table. So we're going to spend some time on this slide. You have this image in your notes. So now we're definitely back to our workbook content that is testable. Here we have a periodic table. It has a little bit more information than the one that you have at the back of your workbook. The one at the back of the workbook, the back cover, that's the one that you should do all your practice problems with. That's the one that you get for your tests and exams. That's the one that I have hanging in my office as well. This one here is also highlighting the different S, P, D, F blocks that we talked about before. So last class, we identified the S block. So our alkali metals, and our alkaline earth metals. Now you do want to know the names of the groups on the periodic table. Not because we like making you memorize stuff, but so that when we talk about an alkali metal, you know what we're talking about. So we can use the same scientific language. So we have the S block on the left-hand side. Remember, the S starts at 1s, 2s, 3s, and as we go down the periodic table, it increases. All the elements in the same group, so for example, group 1 on the periodic table, hydrogen, lithium, sodium, we have pictures of them here on the notes. They all have one valence electron in the highest principal quantum number orbital. So 1s1. 2s1, 3s1, 4s1, and so on. We know now that that's why they have very similar chemical properties. They tend to react and lose that one electron. They tend to react in a 1-to-1 ratio with the halogens on the other side of the periodic table. Lithium, sodium, potassium, rubidium, cesium, all of these elements tend to be soft, shiny, very reactive metals. When we go over to the alkaline earth metals, they're still in the S block. All of these metals have 2 valence electrons in the S orbitals. So 2 electrons in 1s, 2s, 3s, and so on. And that gives rise to their very similar properties. Magnesium, calcium, strontium, a lot of them tend to lose 2 electrons and form compounds in ratios that allow them to have lost 2 electrons. Then we move over to our P block elements. And we talked about how the P, there is no 1P, but it begins at 2 and 3 and goes down from there. We have PX, PY, PZ, 3 P orbitals. Each holds 2 electrons. That's 6. And the P block is 6 elements wide. Boron, aluminum, gallium, all of these will have 3 valence electrons, which is where the name trials comes from. And then they tend to react in those ratios that allows them to lose 3 electrons. And then the next group with carbon and silicon, these are our tetrals. Maybe it doesn't have an A, something like that. And tet means 4. So we have our 3 group, our 4 group, and then when we get to nitrogen and phosphorus, these ones have a really funky name, and these are called the pnictogens. And this comes from the word to choke. Most of our air is nitrogen gas, N2. About 78% of the air particles in this room are nitrogen. If you breathe in 100% nitrogen, you're gonna choke, right? Because you don't have any oxygen. So people tried to breathe in nitrogen, they would choke, which is where the name choke, chalcogen, or pnictogen comes from. Did I just write down the wrong word? There's our pnictogens, they would choke. Okay, then we get to our next group with oxygen and sulfur, and these ones tend to form a lot of ores, like iron ore or iron sulfide, a lot of rocks and minerals, and these are our chalcogens. And then we get to our halogens. that hopefully you're already familiar with. Those are our fluorine and chlorine and bromine, and these tend to react in a 1-to-1 ratio with our alkali metals, and they tend to have similar properties. Some of them are gases, some of them are liquids, and then we get over here to our noble gases. And our noble gases, this entire group here, has a filled valence shell. So they have all the electrons, a filled octet, if you're just looking at the top 8. They tend to be not very reactive. We know now that some of those larger noble gases can react and they can form compounds and stuff as they get larger, but they were known as noble and being filled with their electrons and done. This was built before people knew about the number of protons and knew about the number of electrons, which is pretty cool. We've talked about groups, the alkali group, the halogen groups. The groups are the vertical columns, which means the periods are the horizontal collections. The way I remember it is women have periods for a week of the month, and that's a horizontal grouping on your calendar. So there's the periods and the groups. Okay, so we have our S block, our P block. The S and the P make up the main group elements. So we're going to talk about some patterns in topic 2.2. Main group means we're talking about the S and the P, which means we're not talking about the transition metals or the D blocks. But these are really important. We will talk about these in part of the conversation. And then we have our F block that tucks in right about here. And these are our inner transition metals. Our inner transition metals are made up of 2 groups, the lanthanides and the actinides. And if you look closely, you'll notice some of these have parentheses around their average atomic mass here. That means that they are synthetic. They were made in a lab. They're not really naturally occurring in an abundance that we could do much with. The other elements on the periodic table, for example, if we look at carbon, it has an atomic number of 6. That's the single number at the top. That's the number of protons. Then it has an average atomic mass of 12.01. That's atomic mass units, or grams per mole. You can learn more about those terms in Chapter 1 self-study as a nice review. 12.01 tells you that's the average atomic mass based on the naturally occurring isotopes. So most carbon is carbon-12. About 1% of carbon is carbon-13. And there are other isotopes as well, which gives you an average atomic mass of 12.01. For elements where we don't have multiple naturally occurring isotopes that we can get like an average calculation from, those masses are just in parentheses, and those are just the mass number that we were able to synthesize. Okay, so we have covered so many aspects of the periodic table. I hope this is the messiest slide that I show you all term, but there are lots of important things to know here. In this topic, 2.2, we're going to learn how, based on knowing where an element is on the periodic table, we can predict some of its properties. So, you have this table in your notes, and we have already chatted about this. The S and the P block, those are our main group elements, and those are the key trends that we're going to be talking about. A lot of these trends have to do with the number of valence electrons. And now we know how to write out electron configurations. We know how to figure out which are the valence ones. Those are the highest N level electrons. Now, if we're talking about the D block elements, the transition metal elements, what's valence? isn't strictly defined by the highest principal quantum number. Those d electrons are sometimes considered valence electrons and can participate in bonding. But for the main group, it's the highest principal quantum number. Okay, so this is just a raise of hands, just a nice quick check. Which of the following elements will have the same number of valence electrons in p orbitals as sulfur? So look at your periodic table, and we'll do a show of hands in just a moment. Okay, and so by show of hands, who says that it is A, B, C, D? And most people went for D, and I'm hoping that's correct. Let's move over here. Yes, selenium is right below sulfur in this group on the periodic table. They have the same number of valence electrons, which means they're going to have a similar reactivity. They're going to react in similar ratios as sulfur. Okay. Put a little star by this topic. Understanding this topic is what's going to help you understand all of the trends that we talk about in this topic. So we're going to spend a little bit longer talking about this effective nuclear charge because it sets the framework for some of the other periodic table trends. Okay, annotations. When we say Z, we're talking about atomic number. This was from your chapter 1 self-study, and you know this from high school. When we know the atomic number, that is telling us the number of protons. If we change the number of protons, we know that we've changed the element. That changes the identity of the element. So we could talk about the atomic number, and we usually do. We can also talk about Z star, which is called the effective nuclear charge. Nuclear charge is like the number of protons, but effective nuclear charge is like this qualifier, the experienced nuclear charge, the in reality, feet on the ground, what it actually feels like kind of nuclear charge. It's the attractive force that a valence electron experiences when it is hanging out in that atom. This concept is best explained with an example. So we're going to look at sulfur. On your periodic table. We just found that one right here. It has an atomic number of 16. So that means it has 16 protons. And if it's neutral, we would expect it to have 16 electrons. Now we can analyze which of these electrons are core and which of them are valence. It's easiest to identify the valence electrons for the main group elements. Those are the ones with the highest N. I can see I have 2 electrons in S, 4 electrons in the 3p, which gives me 6 valence electrons. Anything that's not valence must be core. So that leaves me with 10 core electrons. Well, we're going to draw a little picture here. I'm going to put my 16 protons in my nucleus here and just pretend that I drew 16 protons in there, and you can draw along on the side of your page if you want to. So I have 16 protons, and then I have 10 core electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you might say, yikes, it looks like you drew this in an orbit, like a shell. Wasn't Bohr's model wrong? Yeah, it was. We used the simplest picture to communicate our ideas. I could draw these in S and P and it would get nice and messy. But I'm going to say these are the core electrons. Yes, they're in S and P orbitals, but they are really tight and close to the nucleus. So I'm going to keep it nice and simple and make it look like they're just in a circle. So there are my core electrons, and I have 10 of them. Well, we then have our valence electrons, and I have 6 of those. 1, 2, 3, 4, 5, 6. There are my 6 electrons. Yes, they're in S and p orbitals, but I'm just going to draw them in a nice circle to keep it simple. So I could come along to one of these valence electrons and say, hello, valence electron. It's nice to see you today. How are you doing? Beautiful weather. Love the sunshine. Get outside for a beautiful walk in the leaves. What is your attraction to this nucleus? We see that this nucleus has 16 protons. Are you feeling a full pull of 16 attractiveness to this nucleus? And the electron would say, no, I don't feel a pull of 16 protons because this nucleus is being shielded by these three-dimensional orbitals with electrons. It's being shielded by the core electrons. So this valence electron over here can't experience the full 16 protons because it's being shielded by 10 core electrons. This electron over here that we have just interviewed is actually experiencing an effective nuclear charge, which is Z star. Z star is the atomic number of protons, that's 16, minus the number of core electrons, which is 10. 16 minus 10 is 6. So this electron here is feeling an effective nuclear charge pull of plus 6. Now, based on the way that I've drawn this, I could then come over to this electron here and say, well, how are you doing today? What is your experience of the nuclear charge? What is the effective nuclear charge you are feeling? And it would also say, no, I don't feel a full pull of 16 protons because it's shielded by 10 electrons. I'm only experiencing plus 6 as well. And each of these valence electrons that's much further away from the nucleus has a plus 6 attraction and pull towards the nucleus. So we could continue this conversation. We've just started this example. Determine the effective nuclear charge, or Z star, for nitrogen, sulfur, and calcium. We've already identified sulfur had a plus 6 effective nuclear charge. Now we're going to compare that to the other elements here. What about nitrogen? Well, nitrogen is here on the periodic table. It has an atomic number of 7, so it has 7 protons, 7 electrons if it's a neutral. It has valence electrons and core electrons. If we want to calculate its effective nuclear charge, or Z star, we take the number of protons, which is 7, and subtract the number of core electrons, which is 2, and we can see that the effective nuclear charge on nitrogen is plus 5. That's the pull on those valence electrons. We could do the same thing for calcium on our periodic table. We could calculate its effective nuclear charge. We can see its atomic number is 20, and all of its electrons are core except for those 2 valence electrons. So that means it has 18 core electrons, which gives the experienced effective nuclear charge on the valence electrons as plus 2. So my question for you, which of these elements has the greatest effective nuclear charge? Chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, so we extended it here. 3/4 of us got to chlorine, realizing that it has a +7 effective nuclear charge. Sodium, meanwhile, only +1. We already did sulfur, and aluminum just +3. How did we get that? Well, can you see the pattern starting to happen here? As we go across the main group elements, from the S across a period, all the way over to the end of the P's, we're adding a proton with every step, but the number of core electrons is staying the same. So the experienced effective nuclear charge over here on the alkali and alkaline earth side of the periodic table, those electrons are experiencing like a +1 and a +2 and a +3, +4, +5, +6, +7. And those electrons have a much greater attraction to the nucleus as we move over here. So you can imagine how that's going to impact the size of the atom based on what its effective nuclear charge is, which is our conversation for next class. Have a great day. I will see you on Wednesday.